Hi guys, it's Mrs. Allison. Today we are going to look at another method of integration. And before we do that, I would like you to try both of the warm-up problem and the integrals that are listed below it. So hit pause and then come back when you're done. So let's look at this example. It says that we have a twice differentiable function and its derivatives are continuous. And so the table is given at right, and we are asked to find the integral of x times f double prime of x dx. Okay, now looking at this, I know that I'm going to do it without the bounds in for first. We'll go put the bounds in just a moment. Looking at this, I have the product of functions. And so therefore, I'm going to need to use integration by parts. So I'm going to let u equal x, and I'm going to let dv equal f double prime of x dx. Therefore, du would just equal dx, and v would equal f prime of x, the antiderivative of the double prime. Okay. Rewriting this integral, then, we would get u times v minus the integral of v du. And now when I take the antiderivative here, we get x times f prime of x minus the antiderivative of f prime of x would just be f of x. And normally we would say plus c, but we know that there are bounds on this integral that went from 0 to 2, so let's evaluate this from 0 to 2. Okay, so evaluating this from 0 to 2, I'm going to substitute in using the fundamental theorem of calculus. We would have 2 times f prime of 2 minus f of 2 minus, and now we'll substitute in 0. Well, that first term will be 0 because it will be 0 times f prime of 0 minus f of 0, and now we can make substitutions in from the table. So 2 times the derivative evaluated at 2 would be 2 times negative 1. F at 2 is negative 5. Oops, yeah, sorry. It'd be negative 5, so it was minus negative 5 minus 0 minus 3 for f of 0. So now I just evaluate this, and when we evaluate this we get 6, so we know the answer would be C. Now on to the integrals. The questions are to compare the integrals and determine which one you would use u substitution on, or you could use u substitution on, and how do you know, and then what about the other one? All right, so if we look at the first integral, it's asking if I can use u substitution. Well, let's try it. Typically, we're going to let u represent maybe the more complicated function. So in this case would be x squared plus 10x. And therefore, du would be equal to 2x plus 10 dx. Now, that's not exactly what the numerator says. It says x plus 5, so let's factor out a 2, which leaves us with x plus 5 dx. So I could rewrite this as 1/2 du equals x plus 5 dx. And so I can make a u substitution here. This would be 1/2 the integral of 1 over u du. And I could integrate that. Now I'm not actually going to do that at the moment. We're just talking about when we could use u substitution. All right, what about the next one? Well, this next one, if I let u equal x squared plus 3x minus 10, then du would equal 2x plus 3 dx. And I know I need it to equal 8x plus 82, so maybe I multiply both sides by 4, so we get 4 du equals 8x plus 12 dx. But there's a problem. This doesn't actually work. This doesn't work because we're looking for 8x plus 82. So how do I make up that difference of 70? Where does that plus 70 come from? Can I just add that in? No, I can't. So what now? What do we do now? Well, this leads nicely into what we're going to talk about, the next integration technique. The next integration technique that we are going to talk about is integration by partial fractions. You may actually hear this called also partial fraction decomposition. Partial fraction decomposition. And the goal of this is to break apart a rational expression into the sum of much simpler fractions or much simpler partial fractions, so that when we look at them, if I have my original function, some polynomial divided by another polynomial, I can rewrite this polynomial divided by a polynomial by a constant over a linear factor plus a constant over a linear factor. These are all our partial fractions. So we're decomposing the original fraction. We're breaking it down into fractions that add up to the polynomial. Well, let's look at an example. In this example, we're going to go back to that same problem that we tried to use substitution on and it didn't work. So we're going to find the integral of 8x plus 82 over x squared plus 3x minus 10. Now we know we've already tried use substitution and that didn't work. So the next step would be, in order to use partial fraction decomposition, would be to factor the denominator. So I am going to factor this denominator, and I see that this factors to be x plus 5 times x minus 2 dx. Okay? And partial fraction decomposition says that I can rewrite this fraction to be the sum of a constant divided by the linear term plus a constant divided by the other linear term, dx. So what you should be thinking about is that this looks a lot like adding fractions. It looks like someone has been taking two fractions and adding them together. So my numerator is the sum. When I find common denominators, my numerator becomes 8x plus 82 once I find a common denominator. So there are actually two methods we're going to look at to be able to find partial fractions. We're going to start with the original method that was used for partial fraction decomposition. And what that looks like is a system of equations. So let's go through that idea of the system of equations. So in this, we are going to rewrite this using the two partial fractions. A times x plus 5 plus b times x plus 2. That was a minus 2, sorry. Now, what we're going to do to simplify this is we are going to multiply every term by the common denominator. My goal is to write just one equation. So I'm going to multiply every term by the common denominator. I'm going to multiply this fraction by x plus 5 times x minus 2. I'm going to multiply this fraction by x plus 5 times x minus 2. I'm going to multiply this fraction by x plus 5 times x minus 2. Now my reason in doing this is so that I can rewrite this as 8x plus 82, and I know that the denominators here cancel out. Then it's going to equal a times, well, my denominators over here, my x plus 5s will cancel out. So I will have a times x minus 2. And then in the next term, I'm going to have b times, Well, my x minus 2's cancel out here, so I'm going to have b times x plus 5. What I'm going to do now is I'm going to rewrite this just a little bit. I'm going to distribute, probably I wouldn't write a2, let's write 2a. I'm going to distribute the a and I'm going to distribute the b into both terms. Now what I'm going to do is I'm going to rewrite it one more time, grouping my like terms together. So I'm going to group my ax and my bx together, and my negative 2a, my constant, and my positive 5b together. What I want you to see is that we can write a system of equations that says that if 8x plus 82 needs to equal ax plus bx minus 2a plus 5b, then 8x is going to need to equal ax plus bx. So let's write that down. 8x needs to equal ax plus bx. Well, let's divide out the x's. So 8 needs to equal a plus b. Okay, there's one equation. Now, if you'll notice then also that if 82 is in that mix, then it's going to have to equal negative 2a plus 5b. So 82 equals negative 2a plus 5b is going to be the other of my equations. So let's write what this system looks like. Right now the system says 8 equals a plus b, and 82 equals negative 2a plus 5b. Well, if you remember from our system work, I'm going to multiply this top equation by 2. So I get, oops, I don't either. I get 16 equals 2a plus 2b. And then I have 82 equals negative 2a plus 5b. And now I can eliminate one of my variables. Adding together, we get 98 equals 7b, which means b equals 14. And substituting that back into the 8 equals a plus b, we get that a equals negative 6. So here are my two terms. So if I go and rewrite this according to what I just found, if I go break down my original rational expression, that 8x plus 82 over x squared plus 3x minus 10, I can decompose it into the fractions negative 6, which is a, over x plus 5, plus 14 over x minus 2. So this is the fraction decomposition. Now I'm not actually going to integrate it just yet. I want to show you one other method. Now before we go to the second method, what I want to do is I want to show you why this works. I want to prove to you that this fraction decomposition actually gives us the fraction we're trying to find. Okay, so I'm going to do that in a different color. Let's do that in purple. We are going to take this fraction that is negative 6 over x plus 5 plus 14 over x minus 2. And I want to show you that if we were to combine these two, meaning find a common denominator and combine them, we would end up with the 8x plus 82 over, 8x plus 82 over x squared plus 3x minus 10. Here's what that looks like. We would need a common denominator. So my common denominator would be the expression x plus 5 times x minus 2. So I'd need to multiply both of these by x minus 2 and both of numerator and denominator of this fraction by the x plus 5. So in the numerator on this left-hand side, I would have negative 6x plus 12 over x plus 5 times x minus 2. We know that factors to be the x squared plus 3x minus 10, so that's not the question. And if I multiply 14 by x plus 5, we get 14x plus 14 times 5 is 70, And so we get x plus 5 times x minus 2. Now that they have common denominators, I can combine the like terms. So I have negative 6x and 14x to give me 8x. And I have positive 12 and positive 70 to give me positive 82 over x plus 5 times x minus 2. So when we use partial fraction decomposition, we are breaking it down into two things that add together and give us the fraction that we had before. Now let's look at that second method, the Heavyside method. And really the Heavyside method, named after Oliver Heavyside, is just a shortcut for our systems of equations. So when we begin this method, actually, we are going to go back here. So remember in this step, this system of equations, we factored, and then we multiplied everything by that common denominator. And then we got this expression that was 8x plus 82 equals a times x minus 2 plus b times x plus 5. We feel good about this step, correct? That is where we're going to start the Heavyside method. So in the Heavyside method, I'm just going to begin, and I would normally go through all the process that we did up there, but since we've already done it, I'm going to begin at the place where I have 8x plus 82 equals a times x minus 2 plus b times x plus 5. Now, what Heavyside found was that every time he was doing these systems of equations, that they reduced based off of the fact that one of our factors eliminated, it became 0. So to do that, what we're going to do is we're going to look at the two factors that make up our denominator, and we're going to choose x values to eliminate either a or b. The x values that we're going to choose are based off of these factors, these linear factors. So in this example, I might let x equal 2. Because if I let x equal 2 and I plug 2 into this 8x plus 82 equals a times 2 minus 2 plus b times 2 plus 5, what you'll see is when I simplify this, I get 98 equals, well, my a term disappears, or I've eliminated it. But b would be b times 7, and when I solve, I get b equals 14. What do you know? It's the same b value we had before. So the other x value that I would choose in this example is I would let x equal negative 5. I would choose x to equal negative 5 because negative 5, when I substitute it into this equation, eliminates my b. So we're basically trying to get rid of a and we're trying to get rid of b in both situations. So we choose our x values. While the arbitrary, Heavyside noticed that every time we used an x value that was the solution to one of our factors, that we were able to solve for either a or b. So it's kind of like a shortcut of a system of equations. So on this one, we would get 42 equals a times negative 7, which means a equals negative 6. So the same partial fraction decomposition that we got before. Well, now let's look at the integration part of this. Let's look at the integration part of this. So if I rewrite this integral, I would rewrite it in its fraction decomposition that we looked at above, which was negative 6 over x plus 5 plus 14 over x minus 2 dx. Now, hopefully you'll start to see the pattern of these, but I'm going to rewrite this just a little bit before. Remember that if I'm adding two functions together while integrating, I can actually break up this integral to say the integral of negative 6 over x plus 5 dx plus the integral of 14 over x minus 2 dx. And remember, we also said that we can pull out any constants that are being multiplied just to simplify our integral a little bit. So we would get negative 6 times the integral of 1 over x plus 5 dx plus 14 times the integral of 1 over x minus 2 dx. Now these become much more straightforward integrals. hopefully what you recognize is that this, the antiderivative of 1 over x plus 5, is actually a natural log. So we would get negative 6 times the natural log of the absolute value of x plus 5 plus 14 times the natural log of the absolute value of x minus 2. And we would need the plus c because it was an indefinite integral. And we have just integrated that rational function for which we couldn't use u substitution. Okay, one of the things I want to tell you is that on the AP exam, you're really only going to have partial fraction integration when the denominators factor into non-repeating linear factors, meaning you're not going to get an x minus 1, 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 or you're not going to get a bunch of crazy terms on the denominator that are like x squared plus 3x minus 5 and things that can't be factored or are not linear. So for the AP exam, that will be the case. Now it is possible to do partial fraction decomposition if the terms in the denominator are not linear. It is possible to do. It does require an extra step, but we're not going to focus on that. We're just going to look at the linear terms. So if you're feeling brave, go ahead and hit pause and try to do a partial fraction decomposition on this next one. Let's try this. So I know factoring this denominator is the first step. So in factoring this denominator, I would have x minus 4 over, that would be x minus 5 times x minus 1, which means that this fraction, x minus 4 over x minus 5, x minus 1, could be rewritten as a over x minus 5 plus b over x minus 1. Now, if I were to multiply, and I typically won't show this, but if I were to multiply everything by x minus 5, x minus 1, the whole way across, that what would happen is when I cancel out the terms that are in common, I would end up with the expression x minus 4 equals a times x minus 1 plus b times x minus 5. Now, I tend to go with the Heavyside method on these partial fractions, especially with these linear terms. So I'm going to start by letting x equal 5, and then we would have 5 minus 4, or 1, equals a times 4 plus b times 0. And so then a would be 1/4. Let's just write that over here. So a is 1/4. And then I'm going to let x equal 1. When I let x equal 1, I get negative 3 equals, the a term goes away, and I have b times negative 4. So b equals positive 3/4. And then when I go to write my integral would be the expression a, so 1/4 over x minus 5, plus b, which was 3/4 over x minus 1 dx. Now I'm going to integrate this. And if you want to separate it, that's fine. If you can look at this and see the pattern, that's okay too. And so my integral of this would be 1/4 times the natural log of the absolute value of x minus 5 plus 3/4 times the natural log of the absolute value of x minus 1 plus c because it's an indefinite integral. All right, how'd you do? Okay, let's look at a little bit harder one, shall we? All right, if you would like to hit pause and try it, go for it. If not, maybe let's get you to the partial fraction decomposition part, the part that breaks it all apart, and look what it looks like, and then you can try it. So, first thing, remember the first thing that I need to do is I need to factor my denominator. So x squared plus 12x plus 12 over x times x squared minus 4. Well, let's do that again. So we get x squared plus 12x plus 12 over x times x plus 2x minus 2. So the breakdown of this is going to look a little bit different. I have 3 terms on the denominator, 3 linear terms. And so if I break this down, I would have a over x plus b over x minus 2 plus c over x plus 2. That's really the tricky part of this one. So if you think you can try it from here, hit pause again. All right, taking a shortcut, I'm going to rewrite this as x squared plus 12x plus 12 equals a. What's going to be a little bit different is this is going to be x minus 2 times x plus 2 plus b times x plus 2 plus c times x minus 2. Now, if we let x equal, let's see, the first one would be 0. Okay, if we let x equal 0, then I get 12 equals a times negative 4, which means a equals negative 3. If we use Heavyside and let x equal positive 2, if we let x equal positive 2, then I get 40 equals, the only term left is b, so that'll be b times 8. So then b has to be 5. And if we let x equal negative 2, I get negative 8 equals, and the only term left will be c, which will be c times 8. And so c equals negative 1. So if I look at the integral of this, I'm going to move over just a little bit. If I look at the integral of this, I will have the integral of negative 3 over x plus, that's a 5 over x minus 2 minus 1 over x plus 2 dx. Integrating this, I will get negative 3 times the natural log of the absolute value of x plus 5 times the natural log of the absolute value of x minus 2 minus 1 times the natural log of the absolute value of x plus 2, oops, ran out of room, plus c. So it wasn't so bad. It's a little bit different in its decomposition. There's a few more factors, and we have to deal with each of those factors. Let's look at one more example. Sometimes, if we can't use U substitution, but we find that the numerator is a higher degree than the denominator, and I would try U substitution, just check. But I'm telling you, this one doesn't work. So if the numerator is higher degree than the denominator, we will need to use long division to reduce the integrand to a polynomial and a proper fraction, one that we can actually use for the partial fraction decomposition. So let's look at what that might look like. First, we're going to start with the long division piece. So we would need to divide x squared minus 6x plus 5 into x cubed minus 9x squared plus 24x minus 17. Doing this long division, this is going to give me x. I'm going to multiply and get x cubed minus 6x squared plus 5x, and I'm going to need to change all of those signs to be able to add them. And so we get negative 3x squared plus 19x. I'll need to bring that down probably. Negative 17. And so x squared goes in there negative 3 times. So negative 3 times x squared is negative 3x squared plus 18x minus 15, but I need to change all of the signs of those. And so I end up with 1x minus 2. And that's my remainder because x squared does not divide into x evenly. So this is my remainder. So really, I could rewrite this integral to be the integral of x minus 3 plus x minus 2 over x squared plus 6x plus 5. Well, we don't really need any fancy way to integrate with x minus 3. We know the integral of that piece. What we don't know is the integral here. This is where my partial fraction is going to come in. So hit pause and try to break this fraction down into a partial fraction. Hopefully you had a chance to look at this, and it looks something like, looks like I liked that factoring a lot this this section. So we get x minus 2 over x minus 5, x minus 1. Didn't we just do that? Yeah, we did up above. Okay, so then this breaks down into a over x minus 5 plus b over x minus 1. And so we get x minus 2 equals a times x minus 1 plus b times x minus 5. Using Heavyside, I'm going to let x equal 5. So we would get 3 equals a times 4. So a equals 3/4. And then I'm going to let x equal 1. So we get -1 equals b times -4. So we get b equals 1/4. So I'm going to rewrite this integral again, and I'm going to scroll over just a little bit. Rewriting this integral again, we get the integral of x minus 3 plus 3/4 over x minus 5 plus 1/4 over x minus 1 dx. And now I can integrate. So now I'm going to integrate this expression. The integral of x is x squared over 2. Integral of -3 would be -3x. The integral of this partial fraction, I'm going to get plus 3/4 times the natural log of the absolute value of x minus 5 plus 1/4 times the natural log, scroll over a little bit more, of the absolute value of x minus 1 plus c. And there is my antiderivative. So sometimes we have to use other techniques to be able to get it into a form we can use partial fractions on. Really, we'll know it's partial fractions because it'll be a ratio that we cannot use u substitution on. All right, you guys, have a great day.